Yeah, though today's going to be one of a live example lecture. So if you can chat about lecture, that'd be fine. If you're talking about the lecture content, but yeah, anything unrelated to content, keep it in Discord until the Q&A. Then Q&A, we can talk about off-topic stuff. That's fine. So let's do this one. So I want to get a more in-depth example using actors today, and I have an example using traffic patterns, which is in the repo, so you can check that out. And it will be part of the lecture question today. So the lecture question today is to expand the functionality of the code of the example that we're going to see today. And this is, I'm kind of proud and disappointed in myself. The first time I have to say this semester, but the grader isn't up yet for this question. I'll get the grader up by the end of the day today. But the grader, the auto lab assignment isn't up. For those of you who do take the deadline seriously still, I'll set the deadline to probably next Tuesday just to reflect that, so you're not stressing out over the deadline passing. But I'll probably set it to next Tuesday so you have plenty of time. This lecture question is quite involved as well, especially compared to Monday and Wednesday's questions. Mondays and Wednesday's questions were really softballs, like let's just get a small taste of actors. This one's the big one for actors, and then next week we'll do WebSockets. We'll do something similar to that. What's next Tuesday mean for lecture question? Lecture question. But so this is the big one for actors though. This is pretty involved. The code we're going to see today is pretty involved. There's a lot going on with it. So if you have questions as we're going through this, make sure you're asking. We'll talk about it. We can have conversations and talk about all this. So, you got Mr. Muff. You got excited. No extension on the homework. With homework, the usual things apply though. Make sure you at least attempt it before that deadline. If you have a good solid attempt in before the deadline, you'll have the makeup opportunity. But make sure if you have anything, make sure you submit whatever you do have before the deadline on Sunday. So I'm not too concerned about the homework deadline since there are generous makeup opportunities in this class. All right, so we're going to see some traffic app today, and we'll talk about that. I'll mostly go through the code. I have a few slides to set up the problem of what the problem is, and then I'll go into the code and talk about and go through the code to show you exactly how we implement that problem. So it'll be like the live coding lectures that I've had before, but I pre-built this one to make sure we have everything there and everything right. But I'll set up the problem and then go into the code. And if you have questions or if you want to see me expand on anything, we can still do it as a live coding thing. So the week 10.traffic package has all the code you'll need to get started. And then what we need to add to this is detours at intersections. So the example itself is going to have cars that travel from intersection to intersection and then wait for green lights to be able to go and then travel through all these intersections. So the cars will navigate a predetermined route and but obey traffic laws at each intersection. So that's what the package does now, the example does now. What we want to add for the lecture question is detours at the intersection. So once the intersection receives a detour message, that intersection, when a car arrives at that intersection, instead of waiting for a green light and then saying, hey, my light's green, you can go now, instead of that functionality, the intersection should tell the car, hey, I'm not functioning right now, you're going to have to go through this detour. That detour is going to be a set of directions that the car is going to have to take to get around this intersection, and that car should follow that detour before resuming its original path. So it should replace that intersection that it was trying to arrive at, replace it with the detour directions, follow the detour, and go along that path. And this isn't completely realistic. The intersections are going to have four directions that it can be approached from: north, south, east, and west. But the detour is going to apply to any direction. So it's not completely realistic, but I don't want this question to get out of hand, which it very easily can. debate in the comments. Maybe it's a little out of hand already, but I want to try to control that, control how much it is. It's not too out of hand, but just given how new actors are to you, this is going to be a tricky one. And then testing that, taking Wednesday. So this is like Monday's content, and then take Wednesday's testing, how to test these actors, and test this new functionality. The sample code does have a sample test, and we'll walk through that and talk about that at length when we go into the code. But write a test to test this detour functionality. So this is what we're faced with. Let's talk about what we have. I sit in this chair so much I can't get comfortable in it anymore. Oh my God, that's cold. So we have two types of actors in this example. Actually, let me set up the question without actor terminology. I'm sure I'll use a little bit of it, but we have two different entities, two different types of objects that are interacting with each other in this example: intersections and cars. Intersections should have the behavior of being two roads that intersect, a east and west road for traffic either traveling east or west, and a north and south road for traffic traveling north and south. We're not going to worry about turning signals, turning lanes, any of that. We're going to simulate a simple intersection where either the light is green for east and west traffic and red for north and south, or green for north and south and red for east and west. These are the two states that the intersection can be in. No yellow lights either. No right on red. We're going to keep this as simplified as possible, but still have something of a traffic simulator. So the light's initially going to be green east to west, and just the way the way it's set up, I know this is going to be a little confusing because when I was writing my stuff, it was a little confusing too. There is a variable called red east west, which is initially set to false, initially set to true. So it looks like it's initially red east to west, but the very first thing that an intersection does is change its light to change that to green. So it's initially green east to west, and then it's going to alternate red and green at some fixed interval. So it's going to initially be green east to west. After that fixed interval, that fixed time delay has passed, we're going to be green north to south. After that interval passes again, we're going to be green east to west again, and it'll keep alternating at that interval to be either green north to south or green east to west. So this is how our intersection is going to work. It's not going to have sensors to see if there's traffic. No fancy features, just strictly the alternating at fixed intervals, green, north-south, or east-west. A car is going to be initialized with a list of directions to follow. Each direction, so each step on its path, when it has these directions, we can think of like if you go to Google Maps and say, I want to go from here to here, you're going to get that list of directions. These are the intersections that you're going to arrive at to follow the path to be able to arrive at your ultimate destination. We're going to have a list of these directions that the car is going to follow, and each direction is going to contain the intersection that you're going to arrive at after following that direction, how much time it's going to take to reach that intersection, and these time intervals will be in milliseconds. The time it's going to take to reach that intersection, and whether you're approaching it from the east or west or north to south, which will represent as a Boolean. So a car, when it's created, is going to follow these directions, and it's going to obey the traffic laws. Each time it arrives at an intersection, it's going to either stop if it's a red light or go if it's a green light. So that's the functionality we want, and we want to build this in an actor system where each intersection, each car, is going to behave independently and concurrently, so we can get this whole simulation up and running and just have all of the entities moving around and behaving independently, instead of trying to get some big update loop that asks everything, okay, hey light, hey intersection, are you changing lights, etc. We're going to avoid all that. We're going to run this concurrently and have each entity only responsible for its own functionality, its own behavior, as we're seeing now. So whenever a car approaches an intersection, and this is where we're going to start thinking of actors a bit. When a car approaches the intersection, it's going to let the intersection know, hey, I'm here. I'm either approaching from the east or west or north or south. So it's going to send a message to that intersection and say, hey, I'm here, and here's the direction I'm moving. And the intersection is going to give a green light to that car. It's going to send a green light message and say, okay, you're ready to go. I'm allowing you to go. You can go through this intersection now. If the light is red when the car arrives at the intersection, it's still going to give that green light eventually, but it's going to wait until the light is actually green before sending that message. So when a car approaches an intersection, it's going to say, intersection, I'm here, and then wait for that green light message. Once it gets the green light message, that car is going to go and proceed to its next direction on its route. It's going to head to that next intersection after that. And there's one piece of functionality that we haven't seen yet that we're going to need to be able to get this functionality the way we want it. I guess not strictly need, but for all practical purposes, to make this practical, we'll need it. Is sending messages with a delay. So now, instead of just saying an actor saying, I want to send a message to another actor, and that's what we did before with our counting example, we just fired off messages, and sometimes when we received a message, we immediately responded with another message, and that's how we got our functionality working. And we had one fixed interval message in our actor system at the system level. We said, continuously send a message to this supervisor, and at fixed intervals, at every 5 seconds, I think I had in the example in the slides. But in Q&A, we changed that example around a bit. But we sent that message at fixed intervals. But now we have this new situation where we're going to want to send a message with a delay. So, for example, when a car needs to proceed to its next intersection, it needs to read the delay, the time it takes to travel from the intersection that it's at to the next intersection. It has that delay that it needs to wait. So it's going to have to wait that amount of delay before sending the next message, which is going to say, hey, you've arrived at this next intersection. Maybe you should check the intersection, see if it's green, and do that procedure that you need to do. So we need to delay messages. We have a few cases, and then the intersections. We could do that with the scheduler that we've seen before, but we're going to use the same solution here to these fixed intervals. So we're going to use this schedule once. Similar syntax to what we saw when we were scheduling a fixed interval, a repeating message. But we're going to do this inside the actor class, not inside our main method. So we're not working with the system here. The system is just setting up all the actors and letting them do their thing in this example. And then the actors have to control the timing a bit. So inside the actor class, we're going to import that actor's context dispatcher, similar to what we did with the intervals that we saw earlier. We're going to have an import statement inside our class. So not at the top of the file. Inside our class, we're going to access the context state variable, which is part of the actor. Anything that extends actor has a context. Import its dispatcher, and that's going to allow us to write this next line of code. If you write this line of code without the import, you're going to get errors, and those errors are not going to say, hey, you need to import context.dispatcher. The autocorrect won't help you here. This is something you do have to actually remember to import this thing. So once you import that dispatcher, you'll be able to use this schedule once method from your contexts system. So we are going up to the system level, but from inside an actor class. Access the scheduler, schedule one event. I should be on the next slide here. Schedule it with some time delay. Specify which actor you're sending this message to, and then the message that you want to send. So we're going to wait this time interval amount of time before sending a change light message to ourself. So this actor is going to send a message to itself in time interval number of milliseconds. We're using self here instead of this self is just a variable that happens to be named self. This is a variable that stores an actor ref to the actor that we're currently working from. So it's a reference to the actor. It's an actor reference to the actor that is this actor. So this, and this it's a little bit subtle, but it is an important difference. This class itself is of type actor, but to send a message, we need an actor ref. We need that actor ref, which can send a message to that actor. We can't work with the actor itself. We have to work with an actor ref, which is an actor that's in a system and can receive messages, can be sent messages. So we need an instance. We need a reference to the. We need a reference to the actor ref for this actor, not the actor itself. The actor itself is in this, and the actor class has this variable self set up for us that has an actor ref, that is the actor ref to this reference. So we have to use self here, not this. Important distinction. And this is common, a common variable name, self. When you want to refer to this, but not quite this, you need some other form, or you need a reference to it outside of the context of that class. This is a common variable name. Or in Python, self is used instead of this, and then they have to use this for other things. Anyway, it's something you'll see from time to time, including right here. So this is how we're going to delay a message, but we're actually sending messages to the actor itself. So this is how we're building a delay. We're having actors send itself a message with a delay, and then respond to that message, react to that message, or react to that event, rather, by doing whatever it needs to do. So it's basically saying, hey, in time interval number of milliseconds, I need to change my light. And this is how we're going to have that delay in the intersections itself. Every time interval number of milliseconds, I'm going to change light. And then when it receives the change light message, it's going to schedule another one of these with the same code. So this code itself will be in the case where we're handling a change light message. Okay, so that's all the setup. Who's ready to see some code? So this, I have mixed feelings about this example. I think it's both pretty straightforward and also very complicated. So I'm interested to see what y'all think. It's your, since it's your first pretty decent sized actor example, I have a feeling a lot of you will think it's way crazy complex. But if you take this one piece at a time, I think you'll find it's not too crazy. But if you're still digesting Mondays and Wednesdays lecture content, which is perfectly understandable given how brand new and different this topic is, it's just going to take a long time to digest all this content, which is why I'm explicitly saying through the deadline that this lecture question is going to take a little bit longer. That and because I don't have the grader up. But even if I had the grader up right now, I was still going to set the deadline to a later date. All right, so let's start with our main class and start just going through this. And please, again, if you have questions, we haven't seen much code. I assume why there's not much chat right now. You're just kind of taking it all in for right now. But if you do have questions, especially if they're specific questions, please stop me, slow me down, let me know. Because I'll have a tendency to just rip through this real quick. And then just start playing with the code. So if you need more explanation, if you want more explanation, please don't hesitate to ask. I'm wondering if chat's frozen right now, or if you're all just overwhelmed. So let's look at the top level, the system itself. There we go. Thank you. Word digest. Okay, cool. That's what I figure. I just want to make sure, especially if chat's froze. What if I'm muted and froze, but nobody can let me know? That'd be awful. All right, so So let's take a look at the top level and how we're going to set this up, and then we'll peek into each one of these classes independently. Oh, by the way, just a quick side note. In the repo, during the Q&A, if you really at the tail end of Q&A, there weren't too many people left, so I'll let everyone watching lecture know. We did go through an example. Oops, here it is. We did go through an example of stocks changing prices and then traders taking a look at those stocks and just randomly purchasing. We just had randomly deciding if you're going to purchase a stock or not, and randomly changing. That wasn't the right code. And randomly changing stocks. So there wasn't logic here, but just to get another example, a more softer example, this would be a good ease-in to today's example, bridging the gap from Monday, Wednesday to today. If you want to get your head around a simpler example, and rewatch that video. That one's there for you. It'd be a lot easier to jump in today's lecture if you have that one under your belt. So just a side note for those of you who missed it, I almost used that one for today's lecture, but I went with the traffic example instead and built a whole new example to get a more real world analogy in here. So since most of you probably aren't stock traders, I don't want to go on that tangent, but I do want to turn that into something at some point. So I'm going to create 4 intersections here, and an intersection in its constructor is going to take the time interval of how long it's going to wait before changing lights, deciding which direction is about to go, which direction is going to have the green light. Yeah, just looking at the code, trying to figure out what's going on. Yeah, thank you, Toadfish. So I'm going to create 4 intersections with different time intervals, and then create a few different routes for my cars to travel through. So the first route is going to go through these intersections right in order. And just before, in case anybody is getting tripped up on this, I have no sense of the actual physical space in this example. I just have arbitrary paths, so don't try to make sense of where these intersections are. Why are you approaching this one from east-west and then this one from north? You're going to rack your brain trying to think of that. I just created intersections and did this for the sake of example, without that physical space being represented. So just so you know, just so you're aware. But I have each intersection, I'm going to travel 1, 2, 3, and then 4, and specify how long it's going to take to each one. So and then I'm going to create 3 cars all following that same route. So each one of these cars is going to start at its initial starting spot, and then it's going to drive to intersection 1, and it takes 5 seconds to arrive before it's going to arrive at intersection 1, and it's going to arrive from intersection 1 from an either east or west direction. So if it's currently a red light east to west, they're going to have to wait. If it's a green light, they can blow right through. This. And yeah, these times are all in milliseconds. That's 1,000th of a second. So 5,000 milliseconds is 5 seconds. So 5 seconds, and this light, it's going to start green east to west, and then every 2 seconds it's going to change. So we can start to kind of analyze this and see what's going on. This is going to start green east to west. In 2 seconds, it's going to turn red east to west and green north to south. And after 4 seconds, it's going to be green east to west again. And then 4 to 5 seconds, it's green east to west. So when these cars arrive at intersection 1, we would expect that to be a green light and to have them blow right through that intersection. They can go right through that since they're arriving east to west. 3 seconds after they get the green light on intersection 1, they're going to arrive at intersection 2 from the north or south direction. When they get the green light there, they're going to travel to intersection 3. It's going to take 8 seconds to get there. And again, the seconds, just to get us to be able to watch this happen. If we had more realistic directions and these were in minutes, we're not going to want to sit there watching the program execute. So 8 seconds it's going to take to get from intersection 2 to intersection 3, arriving from north or south. And then 2 seconds later, after getting the green light at intersection 3, they're going to take 2 seconds to travel to intersection 4. And and arrive from either an east or west direction. That Boolean parameter is the east or west. Prepare yourselves, there's a lot of message types here. The direction is going to be an east or west Boolean, and I'll use that throughout the code. We'll use this a few different times. If the Boolean is true, it means we're arriving from either east or west. If it's false, we're arriving at either north or south. So that's going to determine which state the light has to be in to be able to say if we're allowed to drive through that intersection or not. So we're going to get this list of directions that the car is going to follow, and that's going to be given in the constructor of a car actor. Then I have one more example. I just wanted one car doing something else. So going from intersection 3, 2, 4, 1, 10 seconds to get from its start to intersection 3, 6 seconds to get from 3 to 2, and you can see my lack of a concept of a physical space here. To get from 2 to 3, it takes 8 seconds. To get from 3 to 2, it takes 6 seconds. I mean, maybe that could be the case. Maybe it just takes longer in one direction or not. But there's no consistency there. No intended consistency. Maybe accidental. To get from 2 to 4, we're going to take 1.8 seconds. To get from 4 to 1, 4 seconds. We're arriving from north or south, east or west. So that's the route that this car actor is going to take. Would have been a lot more complicated specifying the specific direction the car would come from. A little bit. I mean, maybe there's a way to do that without being too crazy. But with this example, as I was writing this one up, I think I don't know, I'm kind of excited about this one. So I think I might turn this into a homework at a future semester and do things like that, the direction it comes from. Build a GUI to visualize all the cars moving around in actual physical space. And maybe even tie it into there are 4 cars. The 1, 2, 3, 4. But only 2 routes. So these 3 cars, think of a group of people leaving one location and all traveling to another location all together. And then this car is doing its own thing, following a different path. So I do want to turn this into a homework, and maybe it can be similar to the graph where we implement pathfinding in it as well. I don't know if that might be a little too ambitious for a homework assignment. But yeah, there's a lot of natural ways to expand this one, and it might do some of that expanding over the years, over the semesters. But we have 4 intersections alternating between red and green lights on the 2 roads that are intersecting, and 4 cars that are following these 2 different routes to be able to travel through this space of intersections. Yeah, and if we could have a GUI and actually watch the cars move through a city, and we could even import data from real cities and actually build real roads and real maps, it could be a badass homework. But it would take quite a lot of work to get up and running with the vision that I just described there with real world stuff. But there's potential here. I might work on that over the summer. But this one would take a lot to turn into a really cool homework. But if I ignore physical spaces and stuff, it could be a homework right now. So let's start with... Which one do I want to start with? Let's start with intersection. Intersection is probably a little more straightforward. So let's start with intersection. And the messages, I put, this is something I like to do. Blah, blah, next semester students. I just want to point out that previous semester students, I'm always working on this course, your TAs are saying that about y'all. The class before the TAs, especially before the transition to this new curriculum, new 115, 116, anyone who took it before that transition is saying that we're making moves here. Me and my colleagues, we're all working on our courses and making some really great strides, I think, over the past 5 years. If you went through this curriculum 5 years ago even, It's just not the same as it is today. I think y'all are way more prepared when you graduate, by the time you graduate, than our previous students. We're always working on that. All right, so we have quite a bit of different types of messages being passed. I like to put these all in a single class. When I first introduced actors, and I just put them at the top of the class that we're building, the messages that it's going to respond to. Once we have a more complex system, I like taking all those messages, putting them all in one file, and having them all right in one place so I can see all the message types that can be communicated throughout this system. Yeah, Ruslana took this at the first iteration of the new 116, and yeah, dark times. That's where you hear the horror stories of lecture questions being due at the end of lecture. Like, there were some pretty big structural things that I had to figure out about the course that had to settle down a bit. And in CS itself, yeah, exactly, Linux, Linux. CS is such a changing field that we have to do a lot to keep up. Concurrency was not a topic of discussion. Probably shouldn't have been in the curriculum as recent as 5 years ago. Concurrency is a really new topic now that we have multi-core processors. That's the new norm. Because when you have a single core, like, why not just have one big update loop? There's nothing you can really gain by having concurrency, since everything has to happen sequentially anyway with one processor, with one core. All right, so let's take a look at the intersection and just go through this thing and see how we get an intersection to work. And the big focus here will be on the delay when we want to change which direction is either green or red. That'll be the one we talk about, which is actually at the bottom of this. So we'll get there. So in the constructor, as we saw in the system, whenever we created one of these, we gave it a time interval to say how long it's going to wait before changing the light. We're going to initialize red east to west. This is the part I was saying can be a little confusing if you're not reading very carefully. Initializing a variable red east to west, but the very first thing this actor does is send itself a change light message. So immediately, this is going to, not immediately, but however long it takes the message to process, probably less than a millisecond, this is going to be flipped to false pretty much immediately. So it will be green east to west, and then red north to south. So, but one variable that's going to, a state variable determining the state of the light itself, red, either true, red east to west, and green north to south, or false, green east to west, and red north to south. Then we're going to store lists of all the cars that are waiting in each direction. So if a car arrives at this intersection in a direction where this intersection is red, we're going to add them to a queue. And once we go green in that direction, we're going to notify all the cars that are waiting that they can now go. Send them that green light message and say, you're ready to go, get out of my intersection, head on to the next one. We're going to store those as actor references, expecting those actors to be cars. But if somebody else is curious of when I'm turning green on the east to west direction, whatever, they can do that too. They can just be any actor ref. When a car approaches an intersection, it's going to send an approaching message, either approaching from the north or south, or approaching from the east or west. And this is where we would add a little complexity if we broke this down into all four directions. We would have to have either four different messages here, or an approaching case class which stores the direction as a variable. But either way, we have to have some extra logic here to be able to handle all four directions, which wouldn't be too much, but it would just be a little more clutter. I want to try to compact this example as much as I can. But this is where we would add that. And then in the cars, saying which direction they're going. So if they're arriving from the east or west and we're red in the east or west direction, these cars have to wait. We're not going to send them any message. We're going to add them to our waiting list. And then when we do go green in that direction, that's when we're going to send them the green light message. If we're not red east to west, we must be green east to west, and we're going to send them the green light right away. Not going to add them to any data structures. They're going to say, be flying up to this intersection. They're going to say, hey, intersection, are you green in my direction? And we're going to say, yep, you're green, and they're just going to blow on through. We don't have to keep track of that car at all. If they're approaching from the north or south, same logic. If we're red east to west, we must be green north to south. Give them the green light. Else, we're going to add them to the waiting queue and not give them the green light. Don't tell them it's okay to go. So they're going to know to stop. And then add them to the waiting list. Those people have to wait. Append. So this is some syntactical sugar, I guess. Oh, wrong button. This is the same as... This is the same as this. So we're prepending sender to the beginning of this list, and then reassigning the new list that we just created with this new value prepended to that list that we have. So waiting north to south is going to be a reference to the head, the first node of this list. We're taking that entire list, adding a new node that's going to refer to the previous head, and then updating our head to point to this head. So we're revisiting our linked list stuff. But I assume, I just wanted to talk about linked list, to be honest. I assume you're more referring to the syntax, though. This syntax is the same. I can't do... It's the same exact thing as this. It's just a little shorthand that we can use. Similar to if I have var x of type int equals 10. If I just want to add 5 to 10, you're probably used to this syntax. This plus equals. We're doing the same thing. It's the same idea here, except it's prepend equals. But it's the same idea. It's the same type of shorthand that we see with the plus equals method. And we can see that it does just call prepend. Yeah, and then for this, we're adding, so the sender, whoever asked us, whoever notified us that they're approaching, we're going to put them in the waiting list. So they're in one of these queues, they're waiting in line, waiting either north or southbound. They're waiting for this, waiting at a red light, waiting for the green light. And yeah, sender is the actor that sent this, so presumably a car, but it could be anything. We have to always work with actor refs. We can't say that this actor ref is a reference to a car actor. We actually don't have that ability. We just have actor refs here. But we're presumably adding a car to that list. And then when we do go green, we're going to let them know, hey, it just went green. So you can go now. So we have kind of backlogs of cars waiting in each direction if they arrive when it's red. Once we change lights, we're going to get this change light message. When we get a change light message, if we're red east to west, then we must be going green east to west. And I'm going to have a little bit of print statement so we can see what's going on. We can actually run this and get some information of what's going on in our system. We're going to print going green east to west at intersection self, which is going to print out some long reference, but some unique identifying information. And then anybody waiting to go east to west, if they arrived at a red light east to west, we're going to send them all the green light message. And yeah, bring back some functional programming here. One case where we actually want to use for each, because we are just calling something for its side effects, but the side effect is sending a message, to another actor. So we're going to send all of them the green light, and then blank out that list. We don't need that list anymore. They're not waiting anymore, so they're all gone. If we were not red east to west, we must have been red north to south. So now we're red north to south and about to go green north to south. So we're going green north to south. All those cars waiting north to south, we're going to give them all the green light and then blank out that list so we don't accidentally send them another green light. Yeah. Yep, happy meow. So right here, when we said sender green light, we're sending a green light message. This case object, green light, we're sending a reference of that case object to whoever sent us the approaching north-south message in this case. Whoever sent us that message. And then like a car is going to send that approaching message to the intersection, and when it gets the green light, then it knows to move on to the next intersection in its directions. It can keep going on along its path. We'll get into the car part of that so we can see the other side of this communication. Are intersections in car classes like the supervisor class? That's similar. So either the supervisor or the counter classes, they're all actors is the one big common thread. These are all actors, and actors they're classes, so they can have all of the functionality that classes had, but the only way they're interacting with our other actors is by passing messages. So actors are only interacting with each other by passing messages and then reacting to those messages. And this is the big kind of mind-bending new thing that we're seeing, is this actor has quite a bit of functionality in it, but it's only building that functionality by saying, when I receive a message of this type, do something. And it can be receiving and sending messages at any given time. Like a car might arrive east to west and another car might arrive north to south at pretty much the same time. We don't know what order they're going to arrive. We just know that an intersection, once it has a car arrive, it's going to run this code. When it receives that message, it's going to run this code. When it receives an arriving east-west message, it's going to run this code. So we're reacting to messages is the only functionality we really have here for actors. That's the one huge thing that we're seeing, which is an event-based architecture. The receiving of a message is our event, and then we're reacting to that event in some way. That's how we're getting our event-based architecture. It's just confined to messages in actors, and actually in WebSockets as well, it's going to be confined to messages, but the overarching topic is event-based architectures. All right, so change light. We're going to tell all the cars they can go, and then we're going to change that light. This is a Boolean, so I'm going to set it equal to not itself. So if this is true, not is going to be false, set it to false. If this is false, not is going to be true, set it to true. And then we're going to get to that schedule. So we just changed lights, and we're going to say we need to change lights again. Time flies in these awesome classes, right? You know, that I do. I thought I would get through all of this code and it'd be like 1:30 and I would just be looking for something to do. No, I'm trying to rush the end, trying to get through everything. I thought I'd need a lot of questions to fill up the time. But we're going to schedule this message. We just changed lights, so we need to change lights again after time interval number of milliseconds. So after time interval number of milliseconds, we're going to send this intersection is going to send itself the change light message. So we just changed lights, and then we're going to need to change lights again after time interval number of milliseconds. So this is somewhat reminiscent of a recursive function, where whenever we receive this message, we're going to run some logic, and then cause that event to happen again after some fixed amount of time. So this message, receiving this message, causes this message to be sent and received again. So this is somewhat of an infinite loop, except very importantly, during this time interval where nothing's happening, we're not blocking anything. We're not doing something like thread.sleep and having a whole core just sit there doing nothing. We're just saying, hey, schedule this message to happen at some amount of time. So we have the functionality of an infinite loop here, but we're not jamming anything up, because we're just doing this with concurrent message passing and reacting to events. Yeah, I'll keep talking about it during Q&A time, but I at least want to get through the whole program to have that contained in the lecture time. So I'm going to get through this car class here. So a car, on the other hand, is going to take a list of directions and then follow those directions one at a time. So and it's going to react to the direction message. So these are direction is a case class, and I have a list of them, so I can send these directly as messages. So if I receive a direction, I want to wait however much time it takes to reach that intersection. I'm going to send an approaching message to say that I'm approaching that intersection from either east, west, or north, south to myself, to the same car after that delay. So whenever it receives the direction message, it's saying, okay, what's my next directive? I need to go to this intersection. It's going to take this amount of time, and I'm going to arrive from east, west, or north, south. It's going to schedule that message to be sent to be able to tell that it's approaching that intersection. Check whether it's approaching east or west or north, south, and tell that intersection that it's approaching. To start this path, it's going to send itself the first direction in its list. So when this car is first created, it's going to get its directions, and it's going to send itself that first direction. We need to start heading towards that first intersection right away. It's going to receive that, send that approaching message after this time interval passes, get the approaching message, tell the intersection, and when it tells the intersection, it's either going to get backlogged if it's a red light or get a green light right away. But at some point in the future, it's going to get the green light message. And then if there's still more directions to go, if we haven't arrived at our destination yet, we're going to proceed to the next intersection. We're going to take the head of I have a bug in here, don't I? I'm going to have to fix that. No, my test passed, though. I should have this. It's strange my test passed, though. So when we get the green light, as long as there are more directions to follow, we're going to send ourselves the direction for the next direction that we need to follow, and then remove that first direction from the list. We're going to update our list to point to the tail of the head, where tail is the same as next in our linked list. So I'm going to go to the next reference and update my reference for this list to the next reference from the head, so the second element in the list. If there are no directions left to follow, we've arrived at our destination. We can do, we're done with traffic simulating. And just for testing, something you'll use in the lecture question is this get next direction message, which tells the sender which direction is going to be the next one that's going to be followed. I gotta think about this and make sure this is the behavior I want. Oops, I don't want to debug it. I guess that's fine. And let's see one run of this thing. So we have our 4 intersections set up. They're all initially green, east to west, and then after the time intervals, they're going to start going green north to south. So 3 of them. After 4 seconds, the first 3 are all green north to south. And then after roughly the same time, but happen to be right after, that first intersection is green east to west again. Then we have our first cars arriving. So 10 seconds. After 5 seconds, we have our cars arriving at intersection 1, which should be green. So they're approaching that intersection from east to west. It's green, so they're going to chug right along and head to the next intersection. Our lights are changing. Lights changing. Where our cars are going to approach that next intersection, intersection 2. That intersection was red when it arrived, and once it went green, was it? Maybe that just happened to happen in the middle of that. I haven't walked through all the steps of that. Driving to intersection. Green. Approaching, driving. And then all the cars arrived at their destination, and we just have intersections going on and off. Then I have a sample test. Let me quickly flash this during the official lecture time. Where I have a much simpler example, so we can track what's going on with our with each of these. 2 intersections that are going to go faster just because I'm testing and not manually watching these. Much faster lights. Get directions. Start at the start and go to intersection 1. That's going to take 300 milliseconds, and we're going to arrive from the east or west. This is going to start green east to west, and then it's going to be red east to west from 200 milliseconds to 400 milliseconds. So when this car arrives, we expect it to arrive at a red light at intersection 1, and then have to wait until 400 milliseconds to be able to go. So that's what we're going to test, and we're going to be aware of all the timing here. Create a car going on that route. Get the directions for that car. Since we're asking immediately, we expect the directions to be... This is where I got to think about how I want to set that up. I'll have to update the repo and see how I want that set up. But it should be heading to this intersection, but the beginning of the directions, I'll think about how I want that set up, and I'll update the repo. That'll be the first thing I do in Q&A, so I make sure that update is out there. So you have to repo the repo before you start the lecture question. So I expect that first intersection to be where we're heading right now, and after 350 milliseconds, I expect it to be sitting and waiting at a red light. So it should still be heading to that intersection. The decision I have to make is what exactly that should look like. And then after 100 milliseconds, we should have gotten the green light and be heading to the next direction. So we should be heading over to intersection 2 at that point, and getting this direction here.